Hello everyone. Welcome to the 10th weekly live session of the NPTEL course of Remote Sensing Principles and Applications. Uh, this course is brought to you by NPTM and the NPTEL and the SWAM initiative. I am Abhishek Chakraborty, a PhD student under the Prime Minister's Research Fellowship Scheme in the Interdisciplinary Center for Water Research (ICWR) at IISc Bangalore. And this course is being tutored by Professor Ishwar Rajshekharan from the Department of Civil Engineering in IIT Bombay. First things first, the video recordings of the weekly live sessions taken by me will be made available on the YouTube channel, the link of which we have already distributed to you. The files relevant to the sessions will be made available through a Google Drive folder. The files and the video recordings will be made immediately available after the class. I will try my best to upload them within an hour after the class ends or the live session ends. And finally, if I have actually shown any image and if it's taken from the internet in this weekly live session, they are solely for the education purpose. We don't intend to plagiarize anything. So far, we are done with 9 weekly live sessions out of the 12 for this course, and I've already uploaded all the recordings on the YouTube channel, and this is the link of the spreadsheet, which includes the links for each of the YouTube video as well as the illustrations, whichever illustration I discuss during these video lectures. So they have also been uploaded in this link. So today we are going to solve a few questions, primarily primarily some questions would be primarily on radar remote sensing. Some of them will be basic remote sensing, right from where we began, and some of them will again be about satellite remote sensing, orbital periods, orbital velocity, just like the questions we took up the last time. Okay. So let's see. The first question for the day is: a satellite wishes to orbit the Earth at a height of 100 km above the surface of the Earth. Determine the speed, acceleration, and the orbital period of the satellite. Given we are given that the mass of the Earth is 5.98 times 10 to power 24 kg, and the radius of the Earth is 6.37 times 10 to power 6 meters. Okay, so what? Let me just draw a schematic to illustrate the role of satellite remote sensing. So let this be a sphere. We know that the Earth is not a sphere, factually speaking, but let us just take that assumption for the time being. Okay, let this be the center of the Earth. This dot be the center of the Earth. The satellite, it would certainly rotate around, revolve around the Earth in some direction. Okay, so it will have its own path. Let this dotted line be the path taken by the satellite. So let us suppose this R Earth. Okay, so we know that the fundamental distance between the satellite and the Earth will be actually the distance between the center of masses. We already covered it in the previous weekly live session. So the total distance between them would be the altitude plus the Earth's radius, the center of the masses. So let's find it out. The height is 100 km, which is given, and the radius of the Earth is 6.37 times 10 to the power 6 meters. So what are we given in this problem? We are given that total R, that is the distance between the center of the masses of the satellite and the Earth, would be nothing but radius of the Earth plus the altitude. Okay, of Earth plus the altitude of satellite. So what would it be? It would be 6.37 into 10 power 6 meters plus altitude is 100 kilometers. So 100 into 10 power 3 meters again. So this would be 6.47 into 10 power 6 meters. The distance between their center of the masses. Now M Earth is also given, that is 5.98 times 10 to the power 24 kg. G is 6.673 times 10 to the power minus 11, the universal gravitational constant, Newton meter square per kg square. So it's very straightforward. And what are they asking us? They are asking the speed, the orbital speed, the acceleration, and the orbital period. So what do we need to know? So the unknowns. Just a second, please. Unknowns would be the speed. Speed we don't know what the speed is. What is the acceleration? That also we don't know. And what is the orbital period t? That also we don't know. So we need to find it in this question. Let's now do it. Yeah. Anyway, so this to this distance is r, and r is r earth by plus h. It's pretty evident from it. Okay. Now let's take another slide for this. Okay, so velocity, how did we find out the orbital velocity? Recall from the previous session that we discussed that the orbital velocity is actually derived by equating the net centripetal force acting on the satellite with the net gravity force acting on it, right? So let's do the same. Net centripetal force is equal to the net gravitational force between the two bodies. The gravity would be acting downwards, I mean towards the center of the masses. So m satellite times v square by r is equal to g. It is basically, the gravity force is directly proportional to the multiplication or the product of their masses, that is m sat times m central part of the earth. Okay, I mean mass but acting at the center, that is what I'm showing here. Okay, and it is inversely proportional to the square of the distances. So let's just show it as r square. So v square, what do we get the v square as? 1 r gets cancelled anyways, so v square finally happens to be m sat gets cancelled, g times m central, that is that of the earth, by r, or v is just the square root of this, g m central by r. That is what the expression for the orbital speed would be. Okay, so let's just put the values. This was 6.673, the universal gravitational constant, times 10 per minus 11 newtons meter square per kg square. M is, what was m? 5.98 times 10 to the power 24 kg. This is the thing which we are talking about. 98 times 10 to the power 24 kg divided by r, and r we already found out in the previous part is 6.47 times 10 to the power 6 meters. So let's put that, substitute it, 6.47 into 10 to the power 6 meters. Okay. So when you solve it, the value would come out to be 7.85 into 10 to the power 3 meter per second. So the first part of the question is about finding the v, the orbital velocity. That's done. Now let's proceed to the next part. The next part, as you can see in the problem, is being asked about the acceleration. Okay, so let's take another slide just to go through it. The next slide, the next part of the question is about the acceleration. So acceleration is straightforward, v square by r. Okay, and just substitute the values. So v was 7.85 into 10 to the power 3. 7.85 into 10 to the power 3 square by r. R is, I think, 6.47 times 10 to the power 6. Yes, 6.47 into 10 to the power 6. So what do we get? We get it as 9.52 meter per second square. Okay, so with that we found out the acceleration. The third part actually wants you to know the orbital period. That's interesting. Sorry for this. Yeah. So the third part wants you to find out the orbital period. So we can find it out from the basics of the Kepler's law, which basically relates the orbital period and the distance between the center of the masses of the satellites as this t square by r cube is 4 pi square by g m central. So what do we get? We get t as square root of 4 pi square r cube by g times m central. Okay. So t would be, let's put the values, 4 pi square, r is 6.47 into 10 to the power 6 whole cube by g is 6.673 into 10 to the power minus 11 times 5.98 into 10 to the power 24 kg. Okay. And the answer we get is in seconds, which is the SI unit of time, and it would be just a second. So we get the answer in seconds, that is 5176 seconds, which is nearly equal to 1.44 hours. Divided by 60 and then divided by 60. Okay, so let's move to the next part. A remote sensing radar system with a swath width of 50 km is launched into a polar orbit at 205 km altitude. So it's a 5-part question. A, what is the orbital period? B, what is the orbital velocity? C, how long would it take this system to acquire full coverage at the equator if the instrument is only used on ascending passes? So ascending passes we know already, it's from the south pole to the north pole. Descending pass is the exact opposite. We discussed it in the previous question, previous live session. D, now suppose the same satellite is launched into a 55-degree inclination orbit. How long would it now take to complete global coverage operating on ascending passes only? How about if the radar can operate on both ascending and descending passes? Which of these orbits is most useful for studying ice motions in the Arctic Ocean? So let's solve it. The first is, what is the Okay, So the first part is about the orbital period. So our Earth, uh, we know, is around, let's denote it as RE, is 6378 kilometers or 6400 kilometers also some take. Some people even take it as 6300 kilometers. So anyways, height is height or the altitude is 205 kilometer. So the effective distance would be the distance between the center of the masses. Let us show it as R. It would be RE plus H. So 6378 plus 205 kilometers, and that comes out to be 6583 times 10 to the power 3 meters. So the first thing is done. Now we just need to use the same expression which we found. Okay, so T would be square root of 4 pi square R cube by GM central. So let's put that value here. T is square root of 4 pi square R cube by GM central. T is equal to square root of 4 pi square R cube by GM central. Okay. So let's just put the value. So it is 4 pi square. R cube is 6583 times 10 to the power 3 meters cube by G is 6.673 into 10 to the power minus 11 times M central is 5.98 times 10 to the power 24. So it comes out to be 5312.56 seconds. If you convert into hours, by divided by 60 and then again divided by 60. Okay, so for the first division by 60 converts seconds into minutes, and then another division by 60 converts it into hours. So it would come out to be 1.4757 hours. Okay, the second question, the second part wants you to know the orbital velocity. Very straightforward. So we would be using the same expression which we found in the previous question, square root of Gm central by R, which comes out by balancing the net centripetal force with the gravitational force of the two bodies. So that would be Gm central by R. So this would come out to be 6.673 into 10 to the power minus 11 times M is 5.98 into 10 to the power 24 by R. R is 6583 times 10 to the power 3. Okay, so it comes out to be 7631 meter per second. Now the third part of the question is, how long would it take the system to acquire full coverage at the equator if the instrument is used only on ascending passes? Very interesting question. So we need to acquire full coverage of the equator. That would mean that we need to acquire the complete perimeter size at the equator, or the complete circumferential size of the equator. Circumference we can find out very easily. 2 pi r will give us the circumference around the equator, where r is the radius of the earth around the equator. We are assuming here that the radius of the earth, the earth is spherical, so the radius will remain constant. Nothing changes, at least till this point. When we divide that with the swath of the satellite, we will get the total number of passes. Okay, let me just show it up. Will take another slide just to explain it. So this is the Earth, okay, and this is the equator. This is the equator. We know very well. This is the equator. So the perimeter of equator, this is RE, the radius of the Earth, of equator is 2 pi RE. Very simple so far. 2 pi RE. Okay. And it covers the satellite. When it moves, it covers some swath. Okay. Unit, let us suppose unit distance. This is some unit distance covered by the satellite, which we are terming as the swath in technical terms. Okay, so the what would be the minimum ascending passes to cover the entire equator? Ascending passes number, it would be the perimeter of equator by the swath width. It's very straightforward in that sense. So let's now find out. The perimeter of equator is 2 pi RE. Just give me this. Perimeter of equator is 2 pi RE. So 2 pi times RE. RE was what? 658. 6378. Okay. 6378 into 10 to the power 3 meters. Or when you find it out, it would be 40,074 kilometers in kilometer units. Okay. Now minimum number of passes is perimeter by swath width equal to 40,074 by swath width of 50 kilometers, as was given in the question. The swath width of 50 kilometers, it was already given in the question. So it is nearly equal to 802 passes. Now, what would be the time required? The question actually ask you how long would it take this system to acquire full coverage. They're not asking the number of passes. They're asking how long would it take. So, just multiply the number of passes with the time required to complete one orbit. Okay, and that is how you will get that get the time length. So let's do it. Time needed to acquire the coverage, the calculated coverage so that the time, the global, over the entire equator, that would be number of passes times the orbital time, the time taken to complete one orbit. So it is 802, the number of passes which we found out from the previous part at the very end, 802 times t orbit. T orbit we found out as 5312 seconds. Let's do that. 2 seconds, and if you compare it, if you convert it into days, you will get nearly 49.3 days as the answer. So we are done with this part of the question. Part C, we are done with. Now, what about part D? Now, suppose the same satellite is launched into a 55-degree inclination orbit. Okay, how long would it now take to complete global coverage operating on ascending passes only? How about if the radar can operate on both ascending and descending passes? Uh, just a brief about, just a very interesting storyline about why it is talking about global coverage only on ascending passes. Remember we discussed something like this, that the illumination conditions would be would not be equal when the satellite travels in the ascending pass, ascending versus that of the descending pass. So it can at best take it can at best detect the signals from only one passes. Okay, either the ascending pass or the descending pass. Now, some satellites, I also discussed at the end of previous live session, that some satellites, like the ones which are active, they actually emit their own energies. So illumination is not a constant for them, and that is how they can detect signals, or they can operate on both the ascending and descending buses. That is what the last part of the question wants you to know about. Anyways, the first challenge is to understand how different the satellite would be when it is launched at a 55-degree inclination orbit. Let's do it then. D. So let this be the equator. This would be the effective swath width. In that case, the swath width will change, by the way, because it is at an inclination. This is the original swath width. Okay, so we get that. Again, now in this case, for case D, let's do it on the next page. We don't have enough space, unfortunately. So minimum number of ascending passes in the last case was the perimeter around the equator divided by the swath width. But this time it will not be swath width because it's at an inclination. So it will be the effective swath width. Okay, number of ascending passes to cover entire equator is perimeter of equator divided by the effective swath width. And the effective swath width I already illustrated in the previous slide. It is because it is at an inclination. Okay, so let's take sine theta is the swath width by the altitude. The effective swath width. So h is 50 kilometer effective swath width by sine 55 degree, comes out to be around 61 kilometer effective swath width. It actually increases because of the inclination. Now the perimeter of equator, that doesn't change. Perimeter of equator stays the same, and that is 40,074, I think. Yes, 40,074 kilometer. 40,074 kilometers. Okay. minimum number of ascending passes. What about that? So that would be 40,074 by 61 kilometers. So that is nearly equal to 657 passes. Now what about the time needed to do that? The time is again same. The orbital period multiplied by the number of passes. So time needed to acquire the calculated coverage T global equal to number of passes times orbital period. Okay. Which is number of passes was 657 and orbital period was what 5312 seconds. Okay, 657 times 5312 seconds, so this comes out to be nearly equal to 40.5 days. Okay, so what does change? What does change between the two questions? In this case, the time taken is 40.5 days. In the previous case, it was 49.3 days. Because of inclination, the time taken actually decreases. And why does it happen? Because the effective swath width is actually greater than the swath width, the ordinal swath width. Okay. Now, this question does not end here. This question is also asking whether, what if the satellite can even detect signals on the descending pass? That is what this question asks. Uh, how about if the radar can operate on both ascending and descending passes? This part is still left. So what would happen then? So whatever story which we understood so far was only for the global coverage in case of detection of signals only on ascending passes. What if it can detect on both ascending and descending passes? Then of course the time would be halved. It would be cut short by half. So let's do that now. If both ascending and descending passes are used, the satellite swath crosses the equator twice in every orbit. So that results in cutting short the time by half. So the T global in this case would be whatever we got in the previous example, previous part, 40.5 days, just divided by 2, and it comes out to be nearly equal to 20 days. So look at the improvement. The first case was when we had no inclination. At that case, the global coverage time was 49.3 days, almost 50 days. In the second case, we had some inclination, but the satellite could only detect ascending passes. So the global coverage time was nearly 40 days. Now, when the satellite is very efficient, it can detect both the ascending and descending passes easily. Then the global coverage time is cut short to only 20 days. That is a difference. Massive improvement. Next question. Which of these orbits is most useful for studying ice motions in the Arctic Ocean? Okay. So Arctic Ocean, you know very well. we are talking about part E. This is the Earth. This is the equator. Okay. Equator is actually the largest latitude that we know very well. This would be the North Pole, and near North Pole we have this Arctic Ocean. Arctic Ocean. If you check the map, you will get that. So Arctic Ocean, how should the satellite revolve? I mean, move around the Earth. If you want to know about the dynamics of the Arctic Ocean, ice melting or anything, ice motions of the Arctic Ocean, which is most of the studying ice motions of the Arctic Ocean. Of course, then the satellite has to move over the poles, the North Pole, at least. And what kind of satellite do we call them? The polar orbit. Polar orbit is most useful for studying the ice motions in the Arctic Ocean. Studying ice motions in the Arctic Ocean. Now, next question. Two satellites are launched into polar orbits, one at an altitude of 570 km and one at 277 km. Okay. If the swath width for the 570 km satellite is 160 kilometers, what swath width must the 277 km satellite have in order to acquire the same rate of coverage? Suppose the pixel spacing and resolution is such that each satellite produces data at 30 meter sampling on the Earth's surface and that the pixels have the same dimensions in across and along track. Calculate the data rate for each satellite assuming 8 bit samples and 3 different spectral channels for each. Okay, so it basically, I mean, this question is basically an amalgamation of several concepts. The first one is to understand the swath width. Second one brings us back to the very basics. I think probably the third or the second week of the weekly live sessions, where we calculated the memory requirements. Okay, so it's an amalgamation of these two concepts primarily. Let's see what happens. V is 2 pi r, that is the circumference by the t orbit, the distance by time, or it may be even g re square by r. Okay, so when a satellite is revolving at a particular velocity, re with this and small r with the effective distance between their center of the masses. Okay. So in that case, the velocity of nadir point, that is the point right below the satellite observation, velocity of nadir point is by the radius ratio, r by re, smaller than the orbital velocity, smaller than the orbit velocity. So let's check it out now. So if we want to get equal coverage, so these two should be similar. The rate of coverage, rate of coverages, rates of coverage by the two satellites should be similar. Okay, it's pretty self-explanatory for that reason, by the way. So rate of coverage would be is v, the velocity, times re by r, that is a nadir point, ratio, radius ratio, which we discussed just now, times the swath width. That is the rate of coverage. W is the swath width. Okay, so if we have to assure that there is equal coverage as is asked in the question, same rate of coverage, that is what is asked in the question. So we need to equate it for both the satellites to get same coverage. V1 Re by R1 W1 equal to V2 Re by R2 W2. Okay, Re gets cancelled, so we are left with only V1, V2, R1, R2, W1, W2, and we need to find out W2. W2 is unknown, and that is what the question asks you. So let's take another slide just to explain it. So V1, V1 Re by R1 W1 equal to V2 Re by R2 W2. Okay, so W2, which we don't know so far, W2 is in fact equal to W1. Re gets cancelled anyways. W1 V1 R2 by V2 R1, which is W1. Now V is square root of G Re square by R, the first one itself. So let's do it now. W1 square root of G Re square by R1 times R2 by W2 square root of G Re square by R2 times R1. Okay, so we are left with G gets cancelled again, Re square gets cancelled again, so we are left with W2 equal to W1 times R2 by R1 power 3 by 2. That is what we are left with finally. The answer would be, just put the values, 160 kilometers. R2 is 6655 kilometer, the effective the distance between the center of the masses, and 6948 kilometers. 3 by 2. The answer nearly comes out to be 150 kilometers should this work with. So we are done with the first part of this question. What swath width must be the 277 kilometer satellite have? So from 160 kilometers swath width, we get to a 150 kilometer swath width if the altitude changes. That is the first thing which we learn. Now, the memory requirement part. Okay. data rate of each satellite. So how do we get that? So firstly find the number of lines per second, then multiply by number of samples per line, then multiply with 8 bit per sample to get the bits, and then multiply by 3 channels to get the number of channels. Okay, so that is how we need to find out for each of the satellite. So let's do it. So the satellite 1, it acquires the ground velocity. The ground velocity will be a ratio of the RE by R. Okay, so it is V1 times RE by small r1, which is 6953 meter per second. Now 6953 meter per second divided by 30 meters, that is the pixel length, it brings you to lines per second, 232 lines per second. Now multiply it by the number of samples per line. Okay, so 232 lines per second into, multiply it by the number of samples, meter by 30 meters again. So it is 1236 samples per second. Now multiply it by the number of channels, that is 3, and the number of bits, that is 8 bits. So 1236000 times samples per second times 3 channels times 8 bits per sample. So we get 29.7 megabits per second. That is for satellite 1. What about satellite 2? Let's just do it directly. Similarly, satellite 2 acquires the ground velocity, again RE by R ratio of the satellite 2, equal to V2 times RE by R2 is 7418 meter per second. Now just let's do it directly. 7418 divided by 30 times 15, 1,50,000, then 30, then 3 number of channels, then 8 number of bits. So what do we get? We get 29.7 megabits per second for this. Not a huge, I mean, in fact, the same. Is it the same? Let me check. Have I committed a mistake in calculating it? Should be a bit different. 7418 divided by 30 into 15123 into 3 into 8, 29.7, that is correct. The previous one, 1236 123 into 3 into 8. Okay, so it was 29.66. That was 29.66 in that case, and this is 7418 divided by 30 into 150000 by 30 into 3 into 8, it is 29.67. Just a minor difference. Okay. 29.66 to 29.67. That's it. Only a minute difference. Because the ground velocities are more or less very similar, 6953 versus 7418. Now one question on radar remote sensing. A radar instrument has a range resolution of 10 meter in the slant range direction and an azimuth resolution of 15 meters. Suppose that the pixel spacing is exactly equal to the resolution. Data are processed on the satellite and sent to Earth with 1 byte representing each pixel. What is the ground range resolution at the instrument if it is operated with an incidence angle of 30 degree? How about 60 degree? At what incidence angle should the radar be operated to obtain square pixels on the ground? At 30 degree incidence, if the swath width is 100 km and the velocity of the satellite is 7500 meter per second, what is the instrument data rate in bytes per second or in bits per second? A standard broadcast TV channel transmits about 6 times 10 to the power 6 bits per second. How many channels are needed to transmit the radar picture? Okay, let's move. Let's just draw the schematic of a radar system first. Okay, so let this be like this. Okay, so this is the slant range, this is the ground range, this is the azimuth direction, this is the range direction. This is the geometry of radar system. Okay, so let's see geometry in a better way. So this is theta, we know it already. This is what we call as a slant range resolution. And this is again theta, because this is 90 degree minus theta, so this would be the ground range resolution. Ground range resolution. Okay. Sine theta equal to the slant range. Sine theta is definitely the slant range resolution to the ground range resolution. It's pretty evident from this triangle which we just made. Okay, so R slant range resolution by ground range resolution. Okay, it's very simple. Now the first part actually wants you to know what is the ground range resolution of the instrument if it is operating at with an incidence angle of 30 degree and then at 60 degree. Let's find it out. Okay, so ground range resolution let us denote it as delta G is delta slant range resolution by sine 30 degree. So 10 meters by 0.5, because sine 30 is half, so that is 20 meters. Okay, what if it is at 60 degrees? So it would be sine 60 degree in that case. At theta is 60 degree, delta g is delta s by sine 60 degree, 10 meter by square root of 3 by 2, so we get as 11.55 meters. Okay, now the next part is, at what incidence angle should the radar be operated to obtain square pixels on the ground? Very interesting part, very interesting question. Obtain square pixels on the ground, the ground range resolution must be equal to the azimuth resolution. Okay. So this ground range resolution, this ground range, as you can see, along the direction of the, uh, across track and towards track directions should have the same resolutions basically. So azimuth resolution and the ground range resolution should be similar. Otherwise, this will not happen. The square pixels will not happen. To obtain square pixels on the ground, the ground range resolution must be equal to azimuth resolution, that is equal to 15 meters. Okay, so sine theta is delta s by delta g. We just, doing the same. So that was 10 meters, and this would be 15 meters in that case. So it would be 2 by 3, that corresponds to theta being equal to 41.8 degrees. Now question number C. At 30 degree incidence, if the swath width is 100 kilometers and the velocity of satellite is 7,500 meter per second, what is the instrument data rate in bytes per second? Okay. At theta is 30 degree incidence angle, the ground resolution is delta g is 20 meters. We found it out already in part A. Okay. The number of pixels per azimuth line, let it be NL, equal to 100 kilometer by 20 meters. The swath width is 100 kilometer by 20 meters, so that is 5,000. Okay. The velocity is 7,500 meter per second. So the instrument data rate is what they are asking. Again, memory requirements, same amalgamation concept. At v is equal to 7,500 meter per second and azimuth resolution of 15 meter, the number of lines per second LPS is 7,500 meter per second by the 15 meter azimuth resolution. So we get it as 500 per lines per second. Now the data rate is, just multiply it, lines per second times the lines. Okay, so we will get it as 2.5 MB per second, or 20 into 10 power 6 bits per second. Now, a standard broadcast TV channel transmits about 6 times 10 to the power 6 bits per second. How many channels are needed to transmit the radar picture? Okay. Part D of this question is pretty straightforward. So just divide it by 6 into 10 power 6 bits per second. So it would be around 3.3 TV channels to transmit the radar picture. Okay. Last question of the day is, a remote sensing radar image of an area shows location 1 at pixel location 300 times 300, 300, 300, and location 2 at pixel location 400, 250. Estimate the pixel spacing of this instrument if these locations are 325 meters apart. Okay. So let us just take an approximation of a Cartesian kind of a coordinate. So 300, 300 may be somewhere here if it is 0, 0. Okay, so this may be location 1. What about 400, 250? 400 may be somewhere here, 250 may be somewhere here. So let's take location 2, 400, 250. It may be somewhere here. Estimate the pixel spacing if these two locations are 325 meters apart. So that is 325 meter apart. Okay, so let's just find out the distance by, so the distance we can find out by Pythagoras theorem. D would be nothing but square root of 300 minus 400 square plus 300 minus 250 square. It comes out to be nearly equal to 112 pixels. The units is pixels here, so the units will be consistent. Now what would be the pixel spacing? Pixel spacing equal to delta t, let us say. It would be, the distance between them is 325 meters as is already given, divided by the total number of pixels. So 325 meters by 112 pixels, so that comes out to be nearly 2.9 meters. With that, we are done for the day. We will meet again next Friday for the weekly live session 11 with some more new numerical problems. So let's call it a day for now.